probably at the root of me being here many, many years ago, and so being this field, is this lady that I suppose that probably younger people don't know her, but it's probably
we know her.
You know her. It's a part of British history. I'm not going to judge in any way. Of course, I'm a guest here, British politics, but this is just a fact that in 1980, end of 1985, and beginning of 1986. The government of Mrs. Thatcher announced a significant cut, if I understand well, in the basic science spending. And this caused a big reaction from the British science community. And actually, it's written down here, 1,500 scientists paid for this advertisement on the Times that was published on January 13, 1986. In which, of course, if you go through it, it defends the importance of basic science for United Kingdom in particular. As a result, not of this appeal, but of the cut, a big fusion experiment that was supposed to be built with the aid of European funding in Calais, near Oxford, was cut. And because of this cut, basically the UK government said that we are not anymore interested in that. The European Union opened the possibility to other countries to get this experiment, provided they were providing, of course, money to co-found it. And my country, Italy, at that time decided to enter into this business. And actually, the experiment is this one, which I've been directing for a number of years. And I clearly remember when I was a student, I started, research at the beginning of the 90s. Clearly remember that this enthusiasm about this big experiment coming to Padova that was refused in some way from the United Kingdom. So, in some respect, I'm sort of attached to this country also because of this reason. And also, my first job as a postdoc was in Oxford, was in Calais. So that's another good reason why I'm so close, and I'm happy every time I'm back here. So just starting from a little bit of background, the whole point about a number of the issues that we hear today about energy starts from the very basic facts that we are made by carbon. The fraction of carbon in a tree, in the dry material of the tree, it's around about 50%, so it's a lot. It's a pretty abundant element in living matters, in living objects like us or like trees. And this has a very basic and unavoidable consequence that anytime you burn something that comes from a living object, you burn carbon. You have to do with carbon, and normally the combustion, I use it just for the sake of simplicity, that of methane, but it's the same, just more complicated. The formula for other elements could be wood, coal, or whatever, oil. Every time you do have something, a molecule here that contains carbon. Oh, sorry, I shouldn't go behind this. And so I've been instructed not to go behind the chair, but which combines with oxygen. And that's a very basic principle of combustion. Every time you ignite something, a fossil fuel, you get something like that. And unavoidably, you will get CO2. And since up to now, as you know pretty well, still now, I think around about 80% of our primary energy and around about 60-something% of our electricity is produced on the world level by fossil fuel, then this reaction is happening quite a number of times every second in the world. And that's at the origin, one of the root, of course, of the big problem of greenhouse gases. What I'm going to argue today, it's a different scale for transforming energy. Sometimes I myself use, also when I teach, the word producing energy, which the very second after I say the word, I realize it's wrong, because clearly you don't produce energy, you transform energy. And actually today I want to argue about a different scale at which you transform energy, moving from the chemical scale, which is more or less atomic scale. I just put there as a number 10 to the minus 10. Of course, molecules are even larger, but it's the right order of magnitude. To the nuclear scale. Nuclear scale, it's in the order of 10 to the minus 15. So they're Fermi's meters. So at least 5 to 6 order of magnitude smaller. So the whole story about nuclear energy, it's not the whole story, but a big part of the story is that you move from the molecular scale, from the atomic scale to the nuclear scale. After all the chemical energy that we transform today, it's done at the atomic scale. You could call it combustion, an atomic process, atomic energy to some extent, because you rearranged molecules in the outer levels. So basically, you go from molecules to nuclei. That's what nuclear physics does. And sorry, that's remain with too many vowels. It's Italian, but I think it's quite understandable anyway. The big gain in the process is that per reaction, the gain in energy transformation, it's around about a factor of 10 to the 6, 10 to the 7. So per single reaction. You know very well that every individual chemical reaction, even the methane reaction, release a very tiny amount of energy, very, very tiny amount of energy, which is more or less, if you want to have an order of magnitude, think, and this is, even if you don't have a science background, you remember probably from your high school, the ionization energy from hydrogen atom, which is the Bohr energy, is just a 13.6 electron volt, so 10 electron volt. An electron volt, it's around about 10 to the 9 minus 19 joule. So every single reaction, chemical reaction, you release an energy of the order 10 to the minus 18, more or less, joule. Tiny. But you have a lot of them, of course, because the numbers which are involved are Avogadro numbers, or big numbers of molecules into fuel and whatever. So the big gain in terms of nuclear energy is that, of course, per single reaction, you get a big gain. And on top of that, of course, you don't produce CO2. You can get, I wouldn't say avoid strategic dependence, but maybe control, if possible, strategic dependence in some way. Again, then really I will be quick about physics, but I took very seriously the recommendation by Emilka, and I will say a few words because it's always interesting to talk about we physicists like numbers, and we like order of magnitudes, I should say. Mathematicians like precise numbers. We like order of magnitudes. We weigh events, but in this case, it's pretty reasonable. On the left-hand side, you have an hydrogen atom, and as you said, in order to ionize an hydrogen atom, you just need 13.6 electron volt. And this is a slightly small number, actually. Remember, that's exactly the right number for 1 electron volt is the amount of energy that 1 electron gains in 1 volt energy difference, potential difference. But in order to basically with 13.6 electron volt, you disassemble an atom of hydrogen, or with something similar, maybe 100 times larger, whatever, you disassemble a methane molecule. So you transform something. If you want to go to the nuclear level, and just as an example, I put the alpha particle, it's the nucleus of helium. Then, as you know pretty well, nuclei are held together by a force which is much stronger than the electrostatic force that keeps together molecules. And in fact, to break apart protons and neutrons into an alpha particle, you need something like 28,000 electron volt. So again, the factor of 10 to the 7, more or less, 10 to the 6 between the two processes. So this is, every time you hear about nuclear energy, that's an interesting point. Remember this 10 to the 6. The whole story about nuclear energy is 1 million. just to give a number, 1 million gain per single reaction. And actually, this is explained, by the way, but probably the most popular formula in physics, which is E equal mc squared, the Einstein formula about the equivalence between energy and mass. That most of the time people think is just something, for nerds or for t-shirts. Actually, as a real value, it's used. And in fact, if you weight the 2 protons and the 2 neutrons that you need to put together an alpha particle, and you weight an alpha particle, you will see that the alpha particle is lighter than the individual components. It means that when you break them apart, you get a release. I mean, let's put this in a different way. Alpha particle, it's a sort of storage of energy. It's like, it's like a bottle of hot water that if you leave there, or if you put under your blanket in a cold night, release the heat and hits you. And the alpha particle is basically a storage. A nucleus, not the alpha particle itself. A nucleus is a storage of energy. If you're able to release this energy, you can use it. It's really the same principle that mankind did, about 2 centuries ago. By the way, it started from these places with the Industrial Revolution, with the molecules. Now we want to do it with the nuclei. You know that we have a big variety of nuclei. They are different atomic mass number. You have the periodic table. Nature is designed in such a way that it's energetically favorable either to fuse light nuclei or to break heavy nuclei. And this is shown by this picture here. You see that if you go from here to here, that's hydrogen, lithium, carbon, oxygen. If you move in this direction, the energy is smaller, and is more negative. And if you go in this direction, also you go towards more negative energy. It would be a long story to explain, but basically this plot tells you that if you fuse low mass particles, and you get heavier particles on this side of the periodic table, you gain energy, and the same happens if you do it on this side of atomic tables where the heavy stuff are, like uranium. Of course, these are the 2 processes that probably are familiar to: nuclear fission on the right-hand side, and nuclear fusion on the left-hand side. Good, and which are drafted here. Basically, nuclear fusion is where you fuse together light nuclei. In this case, I took the example we are working with, which is deuterium and tritium. On the other side, fission, it's the one where a neutron hits uranium, in this case, uranium nuclei, and breaks it down, in this case, baryon and krypton. And from this process, energy is released. From an historical perspective, it's interesting that the right-hand side process, the nuclear fusion, was discovered in 1938 and applied for the first time for energy production in the Chicago pile by Enrico Fermi in 1942. And in less than 10 years, in 1951, in the United States, in Idaho, the first fission nuclear power plant was open. It's interesting because it's called EBR-1, and it's a landmark in energy history. It's the first fission power plant that had an electrical output of around about 400 watt. If you see the picture, the original picture, you see this big stuff and 4 light bulbs connected to it. It was lighting 4 light bulbs. But it's interesting because this was a demonstration, but since then, very quickly, then we got in the 70s already a significant fraction of electrical energy. I don't know when in this country first nuclear power plant came, but I suspect around the 70s probably, as probably most of Europe. Anyway, the big difference between the two processes, which also, it's a difference in the way you do it, but also it's a different safety, is that fission basically works on the principle of critical mass. Just to make a long story short, you put together enough fissile uranium and you start the process. And the process self-maintains, which makes it rather simple to make it, and made, unfortunately, very simple to produce a bomb in 1945. But on the other hand, as a problem in terms of safety, because this process can continue even without control. And that's what happened, for example, in Fukushima or in Chernobyl. So it's a process that self-maintains if something goes wrong. As we will see for fusion, the situation is on the opposite side. Fusion is much more difficult to obtain, does not rely on critical mass, relies on a precise tailoring of parameters, but which makes difficult to run it. But on the other hand, it's safe because if for any reason you go away from the perfect condition, the process self-extinguishes itself. But I will say a few more words about that in the future. Okay, I finish about the physics introduction. Now I go more into the conversation that we've been doing with Emilka in the last months, and which is pretty interesting for us. Well, you certainly have known from the news, even if you're not maybe expert in nuclear energy, that there has been a significant conversation recently at, I would say, at least a European level, but certainly at the world level too, about nuclear energy, a sort of nuclear energy renaissance, if you want to call it like that. This all started in 2022, when nuclear energy was included in the EU taxonomy about energy that are needed for the energy transition. A few months later, the war in Ukraine started. That was a big disruption, of course, for all the energy market in Europe. And at the same time, more and more there is knowledge about the effect of the climate changes. So a number of things work together in such a way that the attention towards nuclear energy has definitely increased in the last couple of years. Up to a point that in the summer this year, Italy this year is the interim president of the G7. You know that every year one of the member has the presidency. So Italy is as the lead for this year. So the G7, the annual G7 meeting was held in Italy, in southern Italy. And what is pretty interesting is that if you go online, if you Google for the final report that the Prime Minister and the Presidents wrote, it's around about 30 pages, and a few lines for the very first time ever is dedicated to fusion, which is pretty interesting because up to a couple of years ago, fusion was purely an academic subject. Very interesting, but as you probably know, in the public opinion, something, all right, a dream, something that would always come 30 years ago. It's 30 years in front of us. Well, in July or June, whenever it was, the prime ministers sit together and they decided to dedicate to fusion this part, and also to start a G7 fusion, that working group on fusion, as you can see, that will have its first meeting next week in Italy. On the other side of the ocean, the Biden-Harris administration, more or less in the same time as the taxonomy, launched what they call the Developing a Bold Vision for Commercial Fusion Energy, We are in 1522, involving the scientific and the private world in the United States. And this led really a few months ago, June 6, 2024, to this document, which is also publicly available. If you're interested, it's probably an interesting reading, which is the Fusion Energy Strategy 2024, which is a big commitment for the US government that is putting federal money, but it's relying a lot also on private capitals. One thing that, okay, I will come back to the previous one, that has happened. As I said, there's been two big things: the war in Ukraine and and something that is already happening, of course, but the climate crisis. On top of that, as far as fusion is concerned, a third big event that happened in the last 2 years has been the big involvement of private companies. As I said, until 2021, I would say fusion was really mostly an academic business supported by public money, federal money, governments. Since 2021, more or less 2022, private companies entered the field, but listen, not to produce components for fusion plants. That has always been, companies that were producing components, for fusion plants, but companies that have as a mission to deliver a fusion reactor. So they want to have their own view for making fusion. And this plot is updated to 2022, but if you look now, there is this report on Fusion Industry Association. There are 47 companies that are in the world that are working on that with, and this is pretty interesting, a cumulative budget in the last 2 years, which has been around about private investment over 7 billion euros, which is, on a global scale, even on a national scale, is very tiny money. Very likely a sea carrier costs more than that. A submarine costs more or less the same money. But on a energy scale, R&D, it's a lot. Just to give you a number, the federal budget, U.S. federal budget for fusion was around about another magnitude less per year. So now it's increasing. But so this money really gave a big boost to the sector. And in fact, nowadays we do have around about 143 laboratories, both mostly public, and private around the world. I will come back with this map at the end of the talk, but it's important that you just give an eye on where they are located. You can clearly see that there is a line that's cut, as usual, the north of the world from the south of the world. And this is true also for research on fusion energy, from research and application, which is not necessarily a very good news. And in fact, I will return to this at the end of my talk. Well, let's again go back for a few seconds to physics. We do have a clear example, and Emilka was so kind to set it up so nicely for me today, the sun. The sun works. I would say that the life on our planet, it's due to fusion, because it's due to two things, actually. I should be correct. Fusion and water. Fusion because the sun burns around about 600 million tons of hydrogen per second, and basically produce its energy, the energy that comes to Earth, and allows, together with the greenhouse effect, life on Earth, that keeps Earth temperature around about 40 degrees, thanks to nuclear fusion. The other interesting point, but which is a bit out from actually it's totally out from the content of my talk, but I'm always happy to remind this point, because it's one of the beautiful things of nature. Well, you know about the sun. The sun emits radiation, actually, and the peak of the sun radiation, of the sun spectrum, is in the visible light. That's what we see basically, right? Well, thanks to water, our Earth is basically made of water. It's 70% of the surface or something like that is made of water. Water is an excellent absorber of radiation, right? That's the principle why your microwave oven works, because water absorbs microwave radiation, and you cook food. But water absorbs almost any kind of radiation. The story. Submarines it's very difficult for submarine to communicate underwater, and in the nuclear power station, they put spent fuel in the pool. Remember, in the pools, just because the water is an excellent absorber of X-ray and gamma ray. So water is an excellent absorber, with a notable exception. If you look at the spectrum of absorption of water, it's basically absorbing from the radio waves up to gamma rays, but with a small dip, which is exactly coincident with the visible spectrum of the sun. And the sun and the water are two totally independent systems. There is nothing that connects them. All right. The fact that they coincide so perfectly that the absorption dip of water exactly coincide with the peak of solar spectrum, it's at the origin of the life on this planet, together with fusion. Because thanks to this fact, light can penetrate into water, can produce photosynthesis with algae and cyanobacteria and so on and so forth. You can produce oxygen and so on and so forth. So it's I'm often making this example to my physics students to try to encourage them to study, basic electromagnetism, because it's of course pretty annoying when you have to make the test, but it's also nice to see how it works in such a marvelous way on Earth. Anyway, in the labs we use deuterium and tritium, which are two isotopes of hydrogen. We fuse them, or we like to fuse them, and get an alpha particles, an helium, nucleus, and a neutron. Basically, from this process, the helium and the neutrons are released with kinetic energy, and neutron in particular, as you can see, takes away most of the energy. And this kinetic energy, it's going eventually to heat water and to be transformed into electrical energy through the standard process that you use also in thermal power plant, in gas power plant. So from the difference from a gas power plant, it's in the core, but from outside the device, then it's an almost standard electricity production system. Of course, with the big advantage that being this a nuclear reaction, there is no CO2 production. I'm making a long story short, and I know that I'm sort of putting under the carpet a number of issues that this equation brings with, because most of the narrative, and we come to the discussion that we are doing with Emilka, most of the narrative concentrates on the left side, that deuterium from seawater. If you look at the communication, newspaper, documentaries, one of the big selling points is about fusion is that you do it from seawater, energy from seawater, which is, of course, it's pretty appealing, right? That in that bottle of water, there could be, for example, enough energy for your household for the entire year. But there are other issues. For example, you need tritium. All right, tritium is radioactive. We know it's not terribly radioactive. I mean, it can easily be screened. The big problem with tritium are two. Being an isotope of hydrogen, it can combine in your metabolism. So it's the big risk about to stop the radiation from tritium. Just almost aluminum foil, it's enough. But if you ingest it by mistake, then it fixes in your bones, and then it radiates for 12 years, which is not a good thing. So you have to be very careful. Yeah. You have to be very careful about how you deal it, but you know how to deal it. And even because you bred it, since it has such a short lifetime, 12 years, you bred it directly on board, starting by lithium. Anyway, there are a number of good things and a number of issues in this equation, but we are working on that. From a physics point of view, fusing nuclei requires to win the electrostatic repulsion. Both nuclei are positive charged, so they tend to repel each other. And one way to do it is just by heating them. If you heat nuclei, then you can, if a particle is heated, as a kinetic energy, it's a thermal energy basically, and so it's fast enough that you can overcome the electrostatic barrier. This is called thermonuclear fusion. Thermo comes exactly from this, that you heat your fuel, your hydrogen fuel, you ionize it, and then in this heated condition, particles are more likely to collide. Normally, you can do it in two ways. In one way, which is I'm not going to talk today because it's not my field, is so-called inertial energy. Inertial fusion is when you use laser which are focused on a pellet of hydrogen, and you compress in such a way that you produce fusion. Or you do it in a magnetic way, since these particles are in movement and are charged, you can confine them into this sort of donut-shaped container, which are called tokamak, through magnetic field. That's what we do and what I personally do. Of course, this is a sketch, something real, a few hundred miles from here. It's the JET experiment that it's now under retirement. It operated in Callum. It was a European experiment up to last year. It used to be the largest tokamak in the world, and this gives you more or less the size of one of these tokamaks. A person, it's more or less up to here. So they're pretty big objects. That's the full scale scenes from outside. And probably JET has been part of this narrative about fusion in the last couple of years, since in the last part of its campaign, it operated with deuterium and tritium. Normally, we tend not to use tritium because for the reason I mentioned, that it's kind of hard to manage. So it's not hard, but you just need a regulation. You need safety measures that in most laboratory don't want to take, so don't want to address, because it's simply not needed. You can get physics also using pure deuterium. Anyway, JET did this experiment. They were able to produce for a few seconds energy, not electric energy, but thermal energy. And so this was a big showcase of what really fusion can do. It was really very helpful for our field to show that even if for a short time we can produce some amount, we can convert some amount of thermal energy. That energy was still thermal. It was not converted into electric energy. The next step will be ITER, which is a big device. Also, ITER sometimes comes to the press, which will be built in south of France. That's a cutaway of the machine. I don't know where you can see a person somewhere like here. Yeah, here it is. So it's really big thing, which is under construction in France, as I said. And ITER, you can see here the site, which is now growing even more. It's designed and is built under a joint undertaking by United States, Russia, Korea, Japan, India, European Union, and China. So it's really a big world undertaking. It's a very ambitious experiment. It had a controversial youth when it was started because basically of political reason. They all, putting together around the table all these big 7 parties is not easy. Each of them wanted its own share, so it took some time to make it happening. But now really they're working pretty hard to put together. Of course, ITER has a big ambition. to demonstrate the feasibility of fusion and to produce 500 megawatt of thermal energy for around about an hour. So it's really, it's a holistic approach. It's going to really to address most of the technical issues that you need to solve in order to design a reactor. There are other concepts, like this one, for example, which is much more compact. You look at the same size, same shape, sorry, but it's much smaller. This is, for example, being built in Massachusetts by Commonwealth Fusion System, which is a spin-off of MIT, which is funded by a number. It's a private project, fully private, which is funded a number of companies, including this big Italian energy company, Eni, that it's like BP. It's a company that has its major business in gas and energy and fossil fuel, but that is now investing into fusion. That's one of the examples. It's probably, in my private opinion, the best example of the private attitude. And I go back to the nuclear reactor that ignited 4 bulb lights. ITER has the ambition to solve a large number of problems that are needed for a reactor. ITER is publicly funded, and as you know, government most of the time don't like risk. They want you to build something that is going to last and is going to pay for the money they're investing. Private company have a different attitude. Private company want to do it quick and dirty, if you want to summarize, more or less as it happened to the reactor in 1951. They want to show that it can work. In my opinion, in the opinion of many people, experiment like this probably will work, but they are not designed to solve all problems. So this is good because you can do it much quicker. On the other hand, it's rather sure that after having shown that you can really produce fusion energy for a significant amount of time, you will need to address a number of issues that ITER will address. So they could accelerate the first part of the path, but at some point, everyone will need to get at this at the final point, and so also ITER will be needed. Of course, on the same very quick path, there is STEP in this country, which is another project that you may have heard about, which is again a big investment done on magnetic fusion by the British government. And I want to move towards the end and go back, introduce the final part of my talk that deals with the, say, non-strictly scientific conversation. But before doing that, I just want to spend a minute to tell what I'm personally doing. As I told you before, different from nuclear fission, fusion needs that these parameters are kept very strictly within that margin. And those parameters are density of the plasma, temperature, and the times you confine it. If you, for any reason, you go away from this optimal region, the process self-extinguishes. So this is at the basis of the great safety of fusion. It's a big selling point of fusion with respect to fission. It's also what makes fusion so difficult, because you have always to be on the right spot in order to be energetically efficient. And one of the big problems, it's also that these devices, just for the reason I mentioned you before, that we have such a big energy amplification gain, are managing a large amount of power, large amount of energy. And in a typical tokamak, a fraction of this energy is channeled by the magnetic field into a very narrow region, which is here at the edge of the plasma. Well, remember, the left-hand side is more or less something like around about 12 to 15 meters tall. It's a big thing, it's a four-story building, more or less, so it's big. You may wonder, how big is this lambda Q where all the energy is channeled? Well, this lambda Q is very likely we expect to be of the order of the size of a hand, tens of millimeters at most. This gives origin to a serious problem, which is something that you have probably experienced when you were kids. Focusing. If you go outside today, or even in the summer, you can maybe you put the skin protection cream, but you enjoy a nice summer sunny day. If you use a magnifying glass, the same sun can burn you. Actually, it burns, make flames, and that's because a magnifying glass has a focusing factor of around about 1,000, just roughly speaking. It depends on how it's made, but just as an order of magnitude. So the heat flux, it's amplified, it's focused on a small spot by around about a factor of 1,000. And this is more or less the same that happens in a tokamak reactor. Down there, because this channel is so tiny, all the energy that instead of being spread over the 1,000 square meters of the reactor surface, it's spread over around about 1 to 2 square meters. So it's a gigantic amplification factor, and this is something that we need to cope with. And in order to cope with this issue, that's exactly, Emilka mentioned my work as a chief scientist of DTT. That's exactly why we are building this European device near the capital city of Rome in Italy, which is a public-private enterprise. Is supported mostly by the Italian government, but also by Eni, appunto the private company. And the major goal of this device, that more or less give you the sizes, as you see, they're all similar in terms of shape, which are toroidal. It's going to address this point of focusing. We are going to design magnetic fields, materials, topologies in such a way to spread as much as possible this heat flux and to make it sustainable. Because if we don't spread it, we expect flux surfaces similar, heat fluxes similar to those which are at the surface of the sun. So something which is really unbearable by present materials. But let me now come to my conclusion and introduce basically the reason why I'm here. It was a short time. Of course, I tried to condensate something like 50 years of development in fusion in 50 minutes, which was, of course, not an easy task. But the core message is that in the last couple of years, fusion has made very significant forward movements, both scientifically and technically and financially, and in the financial world. There is a great interest for a number of reasons. There is money flowing in that. And so I would say that if you had asked me 4 to 5 years ago my perspective for fusion, I would have been probably less optimistic than I am now. On the other hand, this opened a new question that up to now, as I said before, fusion was considered at most an academic exercise, and probably by a lot of people also a sort of a dream or a joke. We are pretty much aware about the usual joke that fusion is always 30 years in front of us. Now the situation has changed, because experiment like the spark that I show you can really be game changer, because it's clearly if you are able to show that you really convert a significant amount of energy in a number of private capitals that can be coming to fusion, and the interest of government can drastically increase. Needless to say, in a center that has energy in its title, how much energy is it's important for life, and how less we spend in comparison to other excuse me, to other things. I have always this number in mind that for every dollar we spend on weapons, on arms in general, we spend 1 cent in energy research, energy R&D, which, by the way, includes everything, including fossil fuels, everything. So say in different words, there is a lot of money out there that could go into energy if they wanted. So we might need to consider the fact that part of this money comes to fusion. And this opens a number of questions which are not more technical, of course are still scientific and technical, but are also on the social and ethical front. Because I just want to give you an example that always struck me, and is connected with this map that you probably know pretty well, is the distribution of electricity access in the world. This the fraction of people that has less energy is decreasing, but still we are in the order of 800 million, if I'm not wrong, the last figure I have in mind. The narrative I started my field, thanks to Mrs. Thatcher, as I said before, was that fusion would have been the holy grail of energy. Fusion would have saved the world. We'll get energy from the water. We'll get energy for everyone. The energy problem will be finally solved with fusion. Now that we are coming close, a number of question marks comes, because of course, if you want to be really serious about that, you should not forget that a lot of energy is needed in that part of the world. I don't have time, but maybe some of you have already approached these. I found a very interesting reading, totally neglected by our press in Italy. I don't know, this in England, or in Scotland, in the UK. You know that there was the COP28, I think it was conference in Dubai a few months ago, at the beginning of the year. We heard a lot of things about that, but at least in the press in Italy, no words were said about the position of the African continent at that meeting. And it's pretty interesting that they came there with a document that was signed by all the head of states of the African continent. It's in Nairobi. It's the Nairobi paper. You find it. And, it tells a lot of things. It's a 4 or 5 pages document. It's in English, so it's very easily readable. But one thing that they struck me, now it's not what they say, but what I have understood. They basically tell, well, you have done all this mess, and now you are going to tell us that we have to cut our fossil fuel consumption, then we are already using, if it's good, 100 of what you're using. No way. I mean, we need, in fact, I think that the term they use, differentiated approach or customized approach, I forgot, to the net zero. My recollection of this is that they say we will burn gas for a number of years because, of course, we need to get electricity. So is fusion going to be a solution for this? I remember, this map, remember this one that I showed you before? Well, this wouldn't, I know that it's a very rough comparison, but wouldn't suggest that this is going to be the case. All the technology, all the science of fusion, for good reason, of course, for understandable reason, it's in the rich part of the world. And as I said, I grown scientifically in an environment was fusion, like high energy physics, was a big public enterprise where everyone with good ideas, smart people could go to CERN, propose an experiment, and win the Nobel Prize if they're smart enough. In this new experiment, this is not the case, very likely, because they're private. You cannot go to Rolls-Royce and say, oh, I have a great idea, let me use your, I say Rolls-Royce, whatever private company, of course, because there are a number of issues, like very understandable. They do it for profit, they have to protect their properties, and so on and so forth. So these raise a number of ethical problems, in particular for the academic environment. And I felt very crucial for me to start communicate to my students, that will be the people that will probably see fusion working, not me, but they will see it, these issues, because they have to be aware. And so this is it's ethical in sense of the relationship with the less developed part of the world. But there is another ethical implication in terms of communication. You can be unethical even if you don't say the truth. So it's very interesting that this plot was released a few months ago by the Fusion Industry Association, and it's the association which collects, as I said, the 47 companies. They made a poll between their members, and they asked them, when do you anticipate your company will deliver power to the grid? Be careful. They're not asking them when you will do the deuterium tritium experiment, when your experiment will work. Deliver power to the grid. So they go to the British authority and they sell power to the grid. Well, 22 out of 47, whatever they are, said between 2030 and 2035. I'm not commenting these. Any one of you could have his own idea or her own idea, but it's clear that at least it's very ambitious. Let's put it this way, just to be generous, right? Because it's 5 to 10 years from now. And we were discussing at lunch with Emilka about the fact that if you see any kind of energy that mankind has transformed from the Industrial Revolution to now, wood, coal, oil, gas, solar, there is a curve that takes decades from the very first penetration in the market to the full exploitation. Such an acceleration could, of course, we will see what happens in 5 years. As I said yesterday, I'm not particularly worried for their shareholders. It's their business. If they will become rich, good for them. If they waste all the investments, I'm sorry. Normally, they are not poor people, so it's not a big deal. But the real point is, what about the energy community? What about the world? Because we are, I say we as a community, clearly this message, I'm not giving personally this message, but this is echoing pretty strongly in the community, that fusion is accelerating and is accelerating that much. Are there ethical implications or communication implications also in statement like this? And that's another point that we like to investigate. I should say that it's even more important because fusion, since the very beginning, has been a very open field, a field where even in the Cold War, people worked together from the two blocks. The tokamak was invented by Andrei Sakharov. This gentleman, probably, I don't know, do you know Andrei Sakharov? It's some of you, I mean, it's pretty interesting. He was a Soviet physicist, and he was a super brilliant physicist. Then the war came, and he entered the weapon program of the Soviet Union. So he was the father of the Soviet bomb, and he designed the most powerful weapon that has ever been tested on the Earth. 3,000, the Hiroshima bomb is called the Tsar bomb. Look on the Wikipedia, and you will see. And at the same time, he won the Nobel Prize for Peace. Because, and it's not contradicting, because after that, he became a very strong opponent of the Soviet communist regime. He was exiliated, he was jailed, and so eventually got the Nobel Prize. So anyway, he was a super brilliant physicist, and among the many things he did, he also invented the tokamak. Since I'm in the UK, I like to remember that in the 1969, a team of British scientists was invited to Moscow to cross-check, following the Galilean method, the measurement of temperature in their tokamak, because nobody believed them. It was so exceptional that they asked the British that they were developing the Thomson scattering. At this time, it was the years where the laser was invented. And so the Brits said this idea to use laser light to measure the temperature of these things. So I'm sure this nice cartoon where this trained by scientists from Calm with a number of thermometers go to Moscow. And so just to say, ITER itself was decided in a summit in 1985 by President Gorbachev and President Reagan. So fusion has this long history of collaboration, which needs not to be forgotten. Actually, it's a big value, and so we have to be careful to keep it. But at the same time, we have also to be careful in our relationship with the people, because even if very small, fusion has a small, very, very tiny, but not zero risk of proliferation. In principle, you could use a fusion reactor to breed nuclear fuel for bombs. I mean, it's very tiny, it's probably non-economical, but it's something that you have to be aware of in public conversation. And I think this is, the almost the last one. Well, then there is, I just wanted to sort of give you some flashes about what our conversation deal with. Another point is about communication. Sorry, this is an Italian, but it's a poll that was done at a national level in the spring that came to the press. You know that we are no nuclear country. We shut down all our reactors after Chernobyl, and so we have no nuclear power. But in spring 2024, for the first time, that's a pretty serious poll, 51% of the people say they are favorable nuclear fusion. Of course, it's a poll, so you never know what they would really vote. But it's pretty interesting that among the people who are more favorable are young people, and also for a very good reason, because for a number of people in this room, they were born after Chernobyl. So Chernobyl is, it's history, but really in the past. And so to some extent, it's interesting how the attitude is changing. Okay, and now I conclude. I was a bit long, but I hope I've been able to give you some background, just to say that we have started some work. Milka came to Padova, very interesting. She came and she said, has been a big, it backfired to me because, I'm in a fusion lab. I went to the physics department and she said, we should do an Oxford-style debate. Oh, I said, oh, very good, very good. And the question she proposed, will fusion be on time for energy transition? I said, oh, good. Okay, let's do it. So we convened a pretty big number of people. We had this debate in front of my colleagues, and of course the answer was no. And this is interesting, but I'm joking, but it was very interesting because the audience that participated in this poll was to some extent selected, was biased because they were colleagues and friends. So maybe some of them was really against nuclear, but not really many. And so the global answer is pretty interesting. And so we then organized this school in Venice that worked pretty well, and Milka is there, by the way. It was, we have son also in Venice with a number of people from around the world. And so we really hope to continue this conversation. Thank you. Thank you.